So questions from 3.3 we had. Number 15. Oh, these are great. Expect this as like a test question, okay? Something just like this. So it says birth weights. I'm going to focus this and zoom in a little bit. So it says with the data set, this is listed in Appendix B. It says newborn males have weights of a mean of 3,272.8 grams and a standard deviation of 660.2 grams. Newborn females have weights of a mean of 3,037.1 grams with a standard deviation of 7.06.3 grams. Who has a weight that is more extreme relative to the group from which they came? A male that weighs 1,500 grams or a female that weighs 1,500 grams. So what they mean by this is they want to know who's smaller. Does it make sense that since males weigh a little bit more, you know, you might tend to think that maybe that this might be the smaller number, that the male might be smaller. But also remember that females have a larger standard deviation. So it actually might be the female that's a little bit smaller. Because remember, when we talk about relative standing, we're actually talking about how many standard deviations they are above or below the mean. Is that clear? So that's what I'm going to do. I'm going to figure out how many standard deviation the male is below the mean, and I'm going to figure out how many standard deviations the female is below the mean. And whoever has the bigger number in absolute value is going to be the one that's more extreme. Is that clear? So you can see who's farther away from the mean. So test question totally, okay? Expect something just like this. It might not be exactly this question, but it'll be darn near. To be honest, I've used this question on the test, just to let you know. All right, so what I know is that for males, let me zoom out. For males, I like the whiteboard so much better. I have much better handwriting there. So males and females. Males, I know X bar is equal to 3272.8 grams, and the standard deviation is equal to 660.2. And then the females, X bar is equal to 3037.1 with a standard deviation of 706.3 grams. So what I'm going to do is I'm going to find the z-score for the males, and I'm going to find the z-score for the females. Remember, for a z-score, you do x minus x bar all over s, right? But when you use your x bar and s, you need to do the x bar and s for the males. And then over here, it's the same idea, x minus x bar all over s. But again, you need to use all the information for the females. Well, what I'm testing for both of these is we have somebody that's 1,500 grams, right? In both cases. So I have a male that's 1,500 grams, and I have a female that's 1,500 grams. So I'm going to plug those in the equation just to see what happens. So in this case, it's going to be 1,500 minus this 3272.8, all divided by the standard deviation, which is 660.2. And then for this one, this z-score is going to be the same, 1,500 because of the same weight, 3037.1, all divided by 706.3. So we have to do them separately and see what happens. So remember, if you're going to do this all in one shot, make sure to put the numerator in parentheses, because really this is what that means. If you don't put it in parentheses, you're going to have a big problem there. So 1,500 minus 3272.8 divided by 660.2. Enter. So I get negative 2.69. Negative 2.69. Now remember, z-scores are rounded to the hundredths place. Always to the hundredths. And the reason why is later in the back of the book, we have a table full of z-scores, and that table is only generated using hundredths place. So that's the z-score. It's unitless as well. That's why I don't put units on the z-scores. Because, the top is grams, the bottom is grams, and grams over grams just annihilates each other. So that's why the z-score is meaningless. I mean, the units are meaningless, but that actually means that this is a measure of standard deviations, right? Mm-hmm. So this person is 2.7 standard deviations below the mean, right? 2.69 to be more accurate. So pretty far below the mean. Is this a usual value? Is this would you consider this significantly low? What number is the cutoff for significantly low? -2, yep, and then +2 for significantly high, right? So definitely significantly low. Probably a weight we'd be concerned with, right, nurse? Sorry. Just say yes. Yeah. Okay, so well, remember that's in the low 5%, right? If you look at the two tails, like 95% of the data lives in the middle, right? So that means 2.5% on the left, 2.5% on the right. So this is in the 2.5% as far as low, right? All right, the other one. So the other one we have 1,500 minus 3037.1 divided by 706.3. So I get still significantly low. You agree? -2.78. You guys agree? Still significantly low? Because it's outside that usual value. It's outside that 95%. But what one's lower? The male or the female? Yeah, so this one is more extreme, right? That's more extreme. Good question, by the way. Thanks for asking it, because it's going to be on the test. I like when you ask those. It'd be nice if I just told you all the questions that are on the test, right?
Yeah.
Usually when you guys ask something I find important, I make a big stink out of it, so just pay attention. I give away what's on test. I do it all the time. 21, it asks us to use the sample list and then find the indicated percentile or the quartile. So what I'm looking for is I'm looking for P60. And we have to use that data set, right? Okay, so I'll bring the data set back up, but we have to pop this into the equation. Now, we did this before, so this was for this was 15. This one was 15 in the book, and this one right here is 21 in the book. So it's asking us to find P60. Well, in order to find P60, you have to find the location of the 60th percentile, right? So that's what L means. So you know that it's going to be K over 100 multiplied by N. Mm-hmm. Now this number matters, like if it's a whole number or if it's a decimal, right? If it's a whole number, you use that location and the location right above it, and then you take the mean of the values in those locations, right? But if it's not a whole number, if it's a decimal, you simply round up, and that's the location you choose. So P60 means K is what?
60.
So this is 60 over 100. So really that right there is 60%, right? That's what that part means. So if you're looking for the 60th percentile, you better have a 60% there, and that's what that shows. But I want 60% of how many values? Well, yeah, because there's 50 values here, right? So what I'm doing is I want to go 60% of 50 values. Does that make sense? So I'm trying to get 60% of the way through this chart. So 60% of the 50 values. So 0.6 times, it should be what, 30 on the nose? That makes sense, right? 0.6 times 50?
Yep.
30 on the nose, yep, 30. Is that a whole number, or is that a decimal? Okay, so what I'm going to do is I'm going to take the mean of location 30 and location 31. Now I'm not taking the mean of 30 and 31, I'm taking the mean of the numbers in those positions, okay? So what I have to do is I have to find the 30th and the 31st location.
2.4.
Yeah, so this is 30 right here, and over here is 31. So I'm going to take the mean of 2.4 and 2.5. So that means P60 is going to be the mean of 2.4 and 2.5. So this is going to be 2.45. And this should be in megabits per second?
Yes.
Okay. 31. Listed below in the amounts of strontium-90 is a sample of a simple random sample of baby teeth obtained through where are we at? I lost my value. Obtained from Pennsylvania residents born after 1979. An expected rise in strontium-90 in U.S. I don't know. What's that called? Who knows? So teeth in 1990s. Can you tell I'm a math major? All right. So what I'm going to do is, I think what they're asking us to do is they want us to find the box plot of this data, right?
Yeah.
So this must be how much of the strontium-90 is actually in particular teeth, and who knows where that actually comes from, if that's in millisomethings. So All right, so what I'm going to do is I'm going to make a box plot. In order to make a box plot, what do you have to find? You have to find the min and the max, right? Because those are the last two dashes. You also have to find the quartiles, right? Q1, Q2, Q2. Okay. So what's nice is they have ordered our data from increasing order. So clearly this 128 is my minimum and that 172 is my maximum data value. So I'm going to have to find Q1, Q2, and Q3. Well, how do you find Q1? Q1 is the same thing as what percentile?
25.
Yeah, okay. So this is going to be 30. So Q1 is equal to the 25th percentile. So that means the location is going to be 25 over 100 multiplied by 20. Yeah. So when you count all those values, you get 20 of them. So I need to go 25% of the way through 20 data values. So 0.25 times 20, it should be what? 4? 5. Makes far more sense. Thank you. Whole number or not?
Hit the whole number.
So that means I'm going to have to take the mean of 5 and 6, right? Of location 5 and location 6. So 1, 2, 3, 4, 5. So that's 138 and 142. So P25. I'm sorry, what were the numbers again?
138 plus
142 all divided by 2. So this should be 140. So that's Q1. Q2 would be equal to, again, Q2 is the same thing as P50. So L is going to be 50 over 100. That's right, so this is 10. So I'm going to have to take the mean of 10 and 11, right? So Q2 is going to be the mean of location 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's the mean of 149 and 151. So this is 150. And then Q3 is the same thing as P75. So L is going to be equal to 75 over 100 times 20. So this should be equal to 15. So I need to take location 15 and 16 and take their mean. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So 156 and 161. Thank you, thank you. Okay, so that means when we do our box plot, I can see that the smallest value, I should put this, the min was the smallest value, that's that 128, and the maximum was equal to 172. So that means I'm going to have to go from 128 to 172, and I'm going to have to hit these values on the way. So let's do this. So I have 120, 130, 140, 150, 160, 170, 180. Does that make sense? Then I have to do sorry, that needs to go away. Then I have to do a box plot above that. So 128 is about right here. 172 is right here. So those are your max and min. Q1 was 140, which is right here. Q2 is 150, which is right here. And Q3 is 158, which is going to be right here. You put a box around the quartiles, and then you connect these with the line. So that's a box plot. Holy cow, is that symmetric, isn't it? That looks like a pretty normal distribution, right? Okay. So that's 25% lives here, 25% here, 25% lives here, and 25% lives in between those two dashes. All right.
I just can't believe I finished that.